Alright, the last colligative property we're going to talk about is osmotic pressure. In order to understand osmotic pressure, we need to look at osmosis. So osmosis is the natural, spontaneous process of water moving across a semi-permeable membrane in order to dilute down a solution. Alright, so if we look at the picture on the left, we have a higher concentration of solute on the left side of the membrane compared to the right. So water only is going to move across the membrane to try to dilute down this side so that it matches the other side. Only the solvent can move, solute particles stay where they are. So after osmosis, we've had water move from the right side to the left side, and now the concentrations are roughly the same between both sides. So osmosis will happen without any outside influence until an equilibrium is reached. Osmotic pressure deals with the reverse of this process. Alright, so let's look at how this is going to work. So here's our solvent on the left side this time, our semi-permeable membrane, and then a saline solution on the right side. Water will move from the left side to the right side to dilute down the saline solution so that we have an increase in volume on the right side. This excess volume compared to the other side is called the osmotic pressure head. If we want to then push the water back across the membrane, we have to apply a force. The amount of force that we need in order to push the water across depends on how much water moved and the concentration of the solution. So the greater the concentration of our saline solution here, the more water is going to move across the membrane. The increased amount of water requires a greater force to push the water back. So osmotic pressure then is going to be proportional to the concentration. So this is our equation. Capital Pi here is osmotic pressure, which is equal to our moles of solute per liter of solution, so this is molarity, times our R value, our gas constant, which is 0.0821 liter atmospheres per mole Kelvin. Okay, since we're looking at changes in liters and pressure, we're going to use this value of R. Multiplied by our temperature, which must be in Kelvin. Because of the units of R, we have to use Kelvin for them to cancel out. So osmotic pressure is equal to molarity times R times T. So in our most basic calculation using this idea, we need the molarity and the temperature, since we already know our R value. So we're going to use osmotic pressure is equal to molarity times R times T and fill in what we know. So we have the molarity, we have the R value, and we can convert our temperature from Celsius into Kelvin by adding 273. So then we just have to multiply our numbers across to get our new value. Alright, so 45 plus our 273, so our new temperature is 318 Kelvin, times our R value, times our molarity. So 0.18 atmospheres. So osmotic pressure is going to be measured in atmospheres due to the units of R. So if you remember, the units of R were liter atmospheres per mole Kelvin. When we multiply by Kelvin for our temperature, the Kelvin units cross out. When we multiply by molarity, which is moles per liter, from our concentration, moles and liters cancel out. So we're left with atmospheres for our units. So it's important to remember the units for this. Temperature has to be in Kelvin, concentration has to be molarity, and then our units of osmotic pressure are atmospheres. Alright, we can also use the same idea in an application. So in this case, we're going to use osmotic pressure in order to identify an unknown. So we have an unknown acid solution where 1.23 grams of the unknown acid were added to 150 mils of water to make our solution. We then measure the osmotic pressure to be 0.91 atmospheres at 30 degrees Celsius. Determine the molar mass of the unknown acid. Alright, so if you remember, molar mass is grams per mole. So that's what we're going to be looking for. We already have grams given to us, so all we really need to find from all this is our moles. Alright, so we're going to use osmotic pressure to find the moles. So here's our equation. Now we have osmotic pressure is equal to molarity times R times temperature. So we don't really have moles in here, but moles is part of our molarity. So this is where it's going to come in. So we have 0.91 atmospheres. Our molarity is moles over our liters is 0.150 liters. And I'm getting this from the 150 mils that we have, just converting that to liters, times our R value, times our temperature, which is 30 plus 273. So we have to use Kelvin. Alright, so this will allow us to solve for moles, which is what we need. So we're going to divide both sides by our R and our temperature. Alright, so let's do that first. So 30 plus 273. So our temperature is 303 Kelvin. So 0.91 divided by our temperature divided by our R value gives us 0.036581. And that's going to be equal to our moles over our liters. Alright, so then we can multiply by our volume. So if we take our molarity times our 0.15, we have 0.00548715 moles. Alright, so now that we have our moles, we're going to plug that into our molar mass. So we have 1.23 grams that were given in the question, and now we have our moles. So we can divide to get molar mass. 1.23 divided by our moles, 224 grams per mole. So while this doesn't completely tell us what our acid is, we now know the molar mass of the acid. So we would be able then to narrow it down to some different possibilities. Alright, so with our osmotic pressure, we also have to look at an electrolyte solution. So we have the same basic equation if we have an electrolyte solution. It's still proportional to our molarity times our R times our T. The only difference is going to be that we now have to multiply by our Van't Hoff factor of I. So in this case, I have 3.4 grams of sodium chloride per liter in my seawater. What should the osmotic pressure be at 20 degrees Celsius? Because sodium chloride is an electrolyte, we have to look at the I value, which would be roughly 2, and incorporate that into our calculation. So now we're looking for osmotic pressure. We have 3.4 grams per liter. We need to convert that to moles in order to get molarity. So 3.4 grams, we're going to divide by molar mass of sodium chloride, 58.5 grams per mole. Alright, and since that's per liter, this will give us moles in 1 liter, times our R value, times our temperature, converted to Kelvin. And then last, we have times our I value of 2. So having an electrolyte solution can double or triple or even quadruple your osmotic pressure. Alright, so we have 3.4 divided by molar mass times our R value times our temperature times 2. So we have 2.8 atmospheres for our osmotic pressure. Alright, we'll do one more example looking at an electrolyte solution. And in this one, we're again going to solve for the unknown molar mass. Alright, we have a 2.5 liter solution. We had 9.5 grams of a compound called X, and we've measured the osmotic pressure of the solution at 293 Kelvin. We know that compound X has a Van 't Hoff factor of 4. So what is the molar mass? So again, we're just incorporating that I value again. So molarity times R times T times I. So we're going to do this very much the same way we did the other one. We are looking for molar mass, which is grams per mole. So we're really looking for our moles in this case. So we have our osmotic pressure, 4.3 atmospheres. We're looking for moles. We have 2.5 liters of solution. So we're going to fill this in for our molarity part. We know our R value. Our temperature was 293 Kelvin. And we're told our I value is 4. So now we only have to solve for moles. So we're going to divide by R and T and I. So we'll do that first. 4.3 divided by R divided by temperature and divided by I gives us 0.04469. And that leaves us with moles over 2.5 liters. Alright, because we divided by the R, the T, and the 4 over here. Now we can multiply by the liters. So times our 2.5. .1117 moles. Alright, so now we're going to plug this back in. So we're looking for molar mass. Our grams were 9.5 from the question. Now we know our moles. So we can solve. So 9.5 divided by our moles gives us a molar mass of 85 grams per mole. Alright, so whether we have a non-electrolyte solution, where I would be 1, or an electrolyte solution, we can use either type of equation, just incorporating the I value or not, in order to find osmotic pressure or to find molarity if we know osmotic pressure.